These are the solutions to the linear motion problems I assigned sometime in February, maybe into January. Maybe we'll get to them in February. I don't know. At any rate, after watching the two ed puzzle videos and hopefully writing down the formulas, the 5 big formulas on your formula sheet, these problems I think are pretty useful. And remember, the short solutions are on Physics Classroom Calculator Pad. So the screencast here is just to add a little more depth of understanding. Overall, with these types of problems, one thing you have to be really careful about is trying to memorize one particular way to do things. So oftentimes the problems have 2 or 3 steps. In other words, to get the real answer, you need to know some additional information, which you might have to calculate or get from a graph, and then use that to get the answer. And each of those 2 or 3 steps oftentimes has multiple ways to do them. So oftentimes more than one formula can be used if you're doing it mathematically, or you can choose between graphical and mathematical methods. That's why I can't tell you a set way to solve things. The hint that I can give you is you don't want to just shove a number in where it doesn't belong. In other words, if we're talking about something that's accelerating, you wouldn't just use a formula for constant velocity. And if we have something that is going constant velocity, you shouldn't be looking for an acceleration. All right, with the things being said, let's go ahead. The first one was PC, standing for Physics Classroom 24. It was basically windblown air and can't swim ashore. Love the names from Physics Classroom. They're boating. They accelerate from rest in a boat, in their sailboat, and how far are they from shore after 18 seconds. So we're given the initial information, acceleration, time interval. So this is the formula I'd use. I believe it is formula number 4. And a version of that, simply plug that in and I get that answer. The other way you could do things is to recognize, if you set this up as a velocity time graph, 18 seconds, the slope of the graph is 0.29 meters per second. And after 18 seconds, you'll end up at 5.22 meters per second. The area of this, which is a triangle, which is 1/2 base times height, or height times base, will give you the same answer. So the area of a velocity time graph tells you the displacement, which is basically, in this case, the distance traveled. PC number 2, you've got a drag car racer going 1/4 mile in 4.437 seconds. I convert that to meters here. You're asked to find the average velocity, so that's displacement over time. That gets us this. The next thing you're going to be asked to use is find the acceleration. You might be tempted to use this. The problem is we don't know the final velocity. We know the average velocity, and I think a lot of people would be tempted to plug this in here. And again, you got to be really careful about that. So, and there is a way to do that, I think, using formula 2, but I think the easier way is to simply go back to this formula 4 here. Start from rest, we're going 402.25 meters. We know the time. We can rearrange this algebraically to solve for acceleration. So it's around 41 meters per second squared. Part C, asking for the final velocity. Now we've got this. This is a version of formula 3. So we know our acceleration times time. That gets us our final velocity. So it's accelerating at about 41 meters per second every second and doing that for a little over 4 seconds. PC13 gives you a velocity time graph. It's asking you some questions about Renata gas. Again, funny name. So the acceleration would be the slope of this graph. So that slope is final minus initial velocity, that's 0 minus 18, over final minus initial time, that's 6 minus 0. That gives us negative 3 meters per second squared. For part B, it's asking about the displacement, or in this case it said distance traveled. Well, that's the area of this triangle. And again, the area of a triangle. See if I can, it doesn't have triangles in here, never mind. The area of the triangle is 1/2 height times base. So 1/2, 18 meters per second times 6 seconds, 54 meters. For number 18, you've got a Cessna. It's taking, and it needs to have a takeoff speed of 28 meters per second. So that's actually a final velocity, not an initial velocity. It starts from rest, and it can accelerate at this rate. And it's asking you what's the minimum length of a landing strip. Fun fact, there is some YouTube channels about airports with very short runways. I think St. Bart's in the Caribbean is one. Really neat watching planes take off and land. At any rate, to find displacement when I don't know time, I've got to go and use this, which is formula number 5. And I'm going to solve for this delta x. So 28 squared is 784. 2 times 1.9 is 3.8. So 784 divided by 3.8 gets me a runway length of 206 meters. It's about 650 feet. That's very short, but for a very small plane, that's reasonable. For number 20, I've got someone skiing, which I guess this time of year is not a bad thing to do. Susie loves to ski, or Susie Latovsky loves to ski. I don't know. Again, another weird name. It gives you that she starts at this speed. She ends at 1.8 meters per second as she's gliding across a surface. So she's actually slowing down, and that's the time interval. So I drew a little motion map to help me visualize that. To find her acceleration, final minus initial velocity over time interval, it should be negative. So negative 18.8 meters per second. There's several ways you can now, in the second part, find out how far she travels during this amount of time. I use this, which is a version of Formula 4. By the way, this was a version of Formula 3. So VI times time plus 1/2 AT squared. I get a positive amount here, a negative amount here. So I end up with a net displacement of around 22.3 meters. You could have also used VF squared equals VI squared plus 2AX. Or you could have made a velocity time graph and gotten the area of that. It'd be a little tougher because you'd have to use a triangle and a rectangle, or if you knew how to find the area of a trapezoid. For PC28, this skydiver, look out below, reached a terminal speed of 10.4 meters per second. So he was going after his parachute opened, and he drops his camera. Well, you should know that the acceleration in free fall due to gravity is around 9.8 or 10 meters per second squared. You could use either number there, 9.8 or 10. And the camera's falling 52.1 meters. So it doesn't start from rest, and I don't know the time it takes to fall, and I'm trying to find the final velocity. I smudged up my units there, so I had to redo those. So Formula 5 is the only one I can use. I'm using delta y because it's vertical instead of delta x. It doesn't really matter what the variable is. So I get that VF squared is equal to 1130, so I take the square root of that. It's around 33.6 meters per second. Now I can find the time interval by using Formula 3 and rearranging it algebraically to find the delta t, or the time interval. So my change in velocity divided by the change every second caused by gravity gets me that the camera took 2.36 seconds to fall. I was outside too much shovel and ice today. For PC30, again, you need to think about that we're in free fall. There's a lot of extra information there, but the distance in free fall is 132 meters before the braking area. So that would take about 5.2 seconds. Again, we're using formula number 4, the simplified version of that. To find the final velocity, we're using a version of Formula 3, and we know the time and acceleration. Oh my God. An awful person. I can't believe I did that. I wrote braking spelled incorrectly. That's braking like, something broke. I fixed it. Nobody will know, because nobody will probably listen to this video. You can look at the PDF anyhow. Number 8, I wouldn't expect you to know how to do this very much because we're going to get into projectiles. But I think you can do this, and I wrote down a lot of information. So the big idea with this, and this was not from physics classroom, that's why I just called it 8 because it's the 8th problem, is you want to think about symmetry. So someone's throwing a ball straight up and it's coming back down to the same height. Hopefully it makes sense that at the tippy top of the path, the velocity is 0. And if you're going upwards, but acceleration is pointing down, and then the second half of the trip you're going downwards and acceleration is down, that it will take the same amount of time to go up as it does to come back down, and that's half the total time. And your initial velocity with which you throw the ball up would equal the final velocity with which you would catch the ball on the way down, if it's at the same height, because it's been accelerating for the same time on the way down as it did accelerating negatively on the way up. So I like to split this into half of the problem. So the first half or the second half. And we also know the acceleration is 9.8 meters per second squared downward the whole time. So the only known you're given is the time of the trip is 3.56 seconds. Some things you should know but not directly stated are gravity's acceleration, which is down. You should know that the time up will equal the time down, which is equal half the total time, so that's 1.78 seconds. You should recognize that the initial speed upward would equal the final speed downward, and that the speed or velocity at the top of the path is 0. So if we've done the ball toss lab, by the time we go over these, those are things you should have seen in that lab also. So to find the thrown speed, you only need to think about half the trip. Now, I thought about the second half of the trip. You could have thought of the first half of the trip. So over here, first half of the trip. But I didn't do that because I've got an initial velocity that's non-zero. My acceleration is downward, but my velocity is upward. So one of those, either my initial velocity or acceleration, would have to be negative, and it's easy to make mathematical mistakes with that. Also, on the way down here, I could treat my initial velocity for the second half of the trip as 0, because at the tippy top of the path, it's not moving. So both my velocity would be downward and my acceleration would be downward. And I can think of everything as positive. Okay, so mathematically then, I'd say my initial velocity is 0, acceleration 9.8. The time is half the total time. It's accelerating downward. I use a version of formula 3, a times t. Gonna fix this one as well. So you can see there's a plus in there. Sure you can. And I get 17.44 meters per second. So the throw must also be 17.44 meters per second up. The distance rising would equal the distance falling. So again, I can think only the second half of the trip. If you use the whole time and you do it mathematically correctly, you'll get 0, which makes sense because it ends up at the same height as which it was launched. So here, I'm thinking again of the second half of the trip. Acceleration downward is positive. The distance it's traveling downward is positive. And the time is half the total time that it's falling. So I'm going to use a version of formula 4. And I get 15.5 meters. And that's the maximum height. If you use the entire time with this, you'd get 4 times the distance, around 62 meters. But it wasn't falling for 3.56 seconds, it was falling for 1.78 seconds. All right, that's it, and hopefully if you had questions, that those answers help.